Namaskar. Dear students, now we shall derive the expression for moment of inertia of a disk. Now disk is a plane object. We will have to assume that thickness is negligible as compared to the area. Now we will have to derive the moment of inertia of such a disk of mass m, radius r about its axis. Last time we have observed that just it is not sufficient to say something about the moment of inertia. We will have to specify the axis about which we are interested in the moment of inertia of that object. Therefore, we had the disk of mass m, radius r, and we are interested in its moment of inertia about its axis, that is the axis passing through the center and perpendicular to its plane. Now see, basically if we will have to derive the moment of inertia of any object, then we will have to divide that object into number of elements such that the small element should look like a single particle. For example, what we will have to do? We will have to consider such a small element which is at a distance, say for example small r from the axis of rotation, and we will have to consider the moment of inertia of this. Suppose m dash is the mass of this small element, then we can write m dash r square is the moment of inertia of this element. And then to cover the entire continuous object, continuous system, we will have to integrate. Yes, it is possible. If we think about a polar coordinate system, then we may think about such type of small element and we can integrate over theta to cover the ring and over r to cover the entire disk. But we are not aware about the double integration right now, and therefore we will use the another technique. The another technique is that instead of dividing the system into small element, we shall divide it into the element whose moment of inertia is known to us. That means it may be the object in previous case. Now here we are aware about the moment of inertia of a ring. Okay, just yesterday or last video we have determined the expression for moment of inertia of a ring of radius r, and therefore what I will do? I will divide this disk into number of rings. Correct? Now I will consider one such ring. Now what are the number? How many rings are there? First of all, I will have to consider ring of very small radius, negligibly small, that is 0. Then we will have to consider the ring over that. Then we will have to consider the next ring. Then I will have to consider the next ring, and up to the final ring which is of the radius of about capital R. Means this disk is made up of such concentric rings, right? And for every ring we are aware about the moment of inertia. The expression for the moment of inertia of a ring we have determined in last video, and it is mr square, where m is the mass of that ring and r is the radius of that ring. Now why I am giving the stress on of that ring? Because here capital M is the mass of a disk, but when we consider one such ring, we will have to find mass of that ring and obviously radius of that ring. Therefore here we will consider one such ring. Let this is the ring which is under consideration, whose radius is small r and its thickness is dr or width is dr. Correct? This is width is dr. Therefore, as if this ring is something like this, whose radius is small r and whose thickness or I can say that it is width is dr. Now how can I calculate mass of such type of ring? Radius is fine, radius is r. But by knowing the total mass of a disk m and the radius of that disk r, I can propose a term sigma which is mass per unit area. Correct? Pi r square is the area of this disk, and therefore sigma is the term which is mass per unit area. And if successfully if I calculate the area of this ring, then it is possible to determine mass of that ring. Now what is the area of this ring? Area of this ring, I can write the area of this ring, let it be ds, which is equal to 2 pi r into dr. Correct? 2 pi r is the circumference, dr is the thickness, and therefore 2 pi r dr is the area of this ring. By knowing this area, I can determine mass of this ring to be equal to, it is 2 pi r dr into sigma, because sigma is the areal mass density or surface mass density. It is mass per unit area, and therefore if this is the area, I will have to calculate the mass by multiplying this term by sigma. Therefore this is the mass of that ring. Okay, and therefore I can write now the moment of inertia of one such ring of radius r is 2 pi sigma r dr into r square. Why? Because moment of inertia of a ring, we had an expression with us, and that is equal to mr square, where m is mass of that ring and r is radius of that ring. Therefore for our ring, mass is dm, that is 2 pi sigma r, this is mass, or sorry, 2 pi sigma r dr, and small r is the radius of that ring, therefore it is r square. Correct? That means here we have divided the ring into, here we have divided the disk into number of rings, because we are aware about the moment of inertia of a ring. Already we have derived the expression for moment of inertia of such ring, and therefore we can use the ring as a element to generate the disk. Okay, what I will have to do? I will have to use so many rings. This is the ring of 0 radius, then another ring, and so on from 0 to capital R. Means to generate or to consider a disk, I will have to cover, or I will have to consider such rings from radius 0 to capital R, and therefore the moment of inertia of entire disk is the integration of di, that is we will have to consider the moment of inertia of all such rings where r is to be vary from 0 to capital R. Again remember that just I cannot write it is integration di, because if I is the variable, then integration di is equal to I itself. Correct? I itself, and it is so. But if I will have to find the formula, find a derivation for that, then I will have to write integration is to be over r, and therefore I will have to replace this di by r by substituting this, and hence I can write integration 0 to capital R 2 pi sigma r cube dr. Here it is r, and this r square will be r cube, and therefore it is r cube into dr. Now I will have to solve this. It is very simple. It is 2 pi sigma, then I can write it is r raised to 4 upon 4 from 0 to capital R. Correct? 0 to capital R, and that is nothing but 2 pi sigma. But what is sigma? Sigma is m upon pi r square into, if I substitute the upper limit, then it is capital R square divided by 4. There is no need to substitute lower limit because it is 0, and hence I can write it is r raised to 4 upon 4, and if I simplify this, then this is equal to, we can check, this pi gets cancelled, these 2 2's are 4, r square and r raised to 4 is there, therefore it is r square remains, and it is 1 upon 2 m r square, 1 upon 2 m r square. And this is the formula for moment of inertia of a disk of radius r. Okay, therefore once again in short I can say that to derive the moment of inertia of a disk, I will have to divide the disk into number of concentric rings. Consider one such ring of radius r and thickness or width dr. The area of such ring is ds is equal to 2 pi r dr. The areal mass density or surface mass density is sigma, therefore mass of such ring is equal to 2 pi r dr into sigma. Hence the moment of inertia of one such ring of radius r is di is equal to 2 pi sigma r dr into r square, because the expression for moment of inertia of a ring is mr square, where m is mass of that ring and r is the radius. To find the moment of inertia of an entire disk, I will have to cover, or I will have to consider such rings from radius 0 to capital R. Therefore, I am integrating over R from 0 to capital R of di 0 to R 2 pi sigma R and R square will be R cube dr. Now 2 pi sigma is constant, integration R cube is R raised to 4 upon 4, upper limit is capital R, there is no need to substitute lower limit, hence I can write 2 pi instead of sigma, it is m upon pi R square, then R raised to 4 upon 4 gets cancelled, pi gets cancelled, 2 2s are 4, R square gets cancelled, R square remains, and final expression is half mr square. That is, the moment of inertia of a disk of mass m and radius r about its axis is half mr square. Okay. now suppose in the similar manner, if we are interested in moment of inertia of a cylinder. Now what is the difference between disk and cylinder? Disk has negligible thickness. Actually it should be 0. But if the thickness is 0, then the object will not exist and therefore it is negligible. And cylinder has certain height. Therefore I will write this height is h, the radius is capital R, and I am interested in its moment of inertia about its axis. Therefore what I will have to consider? Consider a cylinder of mass capital M, radius R and height h, and we are interested in its moment of inertia about its axis. Correct? About its axis. Remember that this is very important. Only I cannot tell about the moment of inertia of any object. I will have to specify the axis. Sometimes it happens that if I ask the moment of inertia for a disk, generally we say that it is half mr square. We assume that it is about the axis of the disk itself. But better to specify it. About which axis it is important. Now for that, what can I do? Again, ideally I can consider any small element. This is the element. Then I can rotate this element to consider a ring. Then I can increase the radius of that ring from 0 to capital R to cover the disk. But up to this, we know the moment of inertia. And then what I will have to do? To consider the cylinder, I will have to keep so many disks, one over other, from say for example z is equal to 0 to z is equal to h. And therefore, instead of dividing this cylinder into number of small elements, point element, I will divide this into a disk. Correct? I will divide this into a disk of very small thickness dz, say for example, because this is vertical axis which is assumed to be z axis and which is at height z over the or above the base of the cylinder. Therefore what I will do? I will divide the cylinder into number of disk of radius r. The radius remains same. Thickness dz, correct? Thickness dz at height z from the base, correct? At height z from the base. And therefore, if I am interested in mass of this disk, then what I will have to do? I will have to consider rho, that is volume mass density. It is mass upon volume of this cylinder. What is the volume? It is pi r square h. Pi r square is the area of base, h is the height, and therefore pi r square h is the volume. Total mass divided by volume is the volume mass density. We are aware about this term as a density. Normally we call it as a density, simple density. But here we had considered the expression sigma, that is mass upon area. Therefore this is surface or areal mass density. Last time while determining the moment of inertia of a rod, we had considered the term lambda, that is mass upon length only, and therefore it is linear mass density. Therefore I can use three different symbols to represent linear mass density. Then I may think about the surface mass density, and here now it is volume mass density, and we are familiar with this term as the density itself. Now, what is the volume of this disk? The small volume of this disk is pi r square dz. Check. The area of base is pi r square and dz is the height. Therefore, pi r square dz is the volume of this disk, one such disk. And therefore, mass of one such disk is volume into the density. Therefore, I can write pi r square dz into rho is the mass of that disk. What is the moment of inertia of this disk? We are aware about the formula for moment of inertia of a disk, and that is half m, that is mass of that disk, which is pi r square dz into rho into r square. Now we have derived the formula for the moment of inertia of a disk. See, it is half mass of a disk into square of the radius. Here mass of the disk is dm and therefore it is dm into r square, but I have used the formula for dm as pi r square dz into rho. Okay. To consider the moment of inertia of an entire cylinder, if I will have to cover the cylinder, what I will have to do? I will have to keep such disk one over other. Therefore, I will have to consider the disks from z is equal to 0 to z is equal to h. First disk is to be kept at z is equal to 0, second is at z is equal to 0 plus delta x, third is 0 plus 2 delta x, next is 0 plus 3 delta x, so on, and last one will be at z is equal to h to cover the entire cylinder. And therefore the moment of inertia of an entire cylinder is integration over di, but I will have to integrate over z from 0 to h. Remember that this term is important. Here there is a role of understanding how I can generate the cylinder. I will have to use so many disks one over other. If h is the height and if vertical direction is assumed to be z direction, then I will have to keep the disk from z is equal to 0 to z is equal to h. That means z is equal to 0 to z is equal to h. That is equal to. Now I can take the common terms outside the integration. Therefore it is half pi r raised to 4 rho, and then only there will be integration over z, that is dz, from 0 to h. Now as the variable is z itself, there is no need to write z is equal to 0 once again. Here it is essential to write because the variable seems to be I, but actually we will have to vary z from 0 to h. Correct? Now I will substitute the formula for rho also, and hence I can write it is half pi r raised to 4. Rho is nothing but m divided by pi r square h, and I know that I can skip one term, integration dz is equal to z, and I will have to substitute the upper limit to be h, and hence I can write h only. Okay. Now I will observe that this pi gets cancelled, this h gets cancelled, r square, here it is 1 r square gets cancelled and it is r square, and I can write I is equal to half m r square. Correct. Therefore this is the formula for moment of inertia of a cylinder of mass m, radius r and height h. But the interesting thing is that there is no term of height, that is h is missing here, and it is interesting. That means the moment of inertia of a cylinder will not depend on the height. If I go on increasing the height of this cylinder, just because of increase in mass, the moment of inertia increases. But by keeping the mass constant, if I change the mass distribution only, correct? Because moment of inertia says something about the distribution of mass about the axis. And see here, if I change the mass distribution about in the direction of axis, then moment of inertia will not change. That means suppose there are two cylinders of same mass, but maybe because of the change in the density, height of one cylinder is h and height of other cylinder is twice that of h. Then the moment of inertia will not change. Moment of inertia will remain same. Correct? And that is the interesting thing. And therefore, we will have to conclude that the moment of inertia of a cylinder of mass m and radius r is half mr square. No need to specify its height. What is its height? That is whether it is h or more than that or less than that. Okay. Now this is about the formula for moment of inertia of a cylinder. See, now if I will have to determine the moment of inertia of those objects about different axes, correct? About different axes. Actually, we had the parallel axis theorem That means in case of any random object, it may be the random object having 3 dimensions. If C is the center of mass and this is the axis passing through the center of mass about which the moment of inertia is I0. And if I think about one more axis which is parallel to this axis at a distance A, then the moment of inertia about this new axis I can be given by I is equal to I0 plus ma square, where m is the mass of that object. That means suppose the moment of inertia about the axis passing through the center is I0, which is known to us. And you will observe that in case of the moment of inertia of a cylinder, in case of the moment of inertia of a disc, in case of the moment of inertia about the ring, and in case of the moment of inertia about the rod also, we had derived the expression for moment of inertia about the center itself. Yes. And now if I am interested in moment of inertia about any axis which is parallel to this, then that moment of inertia I can be written as I0 plus m, that is total mass of that system, into a square, where a is the perpendicular distance between those two axes. This theorem is known as the parallel axis theorem. Now, what is perpendicular axis theorem? The name itself suggests that suppose there are 3 axes which are mutually perpendicular to each other. This is x-axis, this is y-axis, and this is z-axis. This is nothing but our Cartesian coordinate system. And if there is laminar object, that means now it is essential to have an object having negligible thickness. See, it should be in the form of a plane object. It is not a 3-dimensional object. Therefore, cylinder cannot be considered here. A ring can be considered because it is in a plane. Disc can be considered. It is in a plane. But a sphere cannot be considered. Block cannot be considered. If there is a distribution of masses in 3 dimensions, that cannot be considered. But if it is the distribution only in 2 dimensions, let it be x and y, then such a object, for such a object, if x and y axis are in the plane of that lamina, this is known as the laminar object or planar object, lamina, then the moment of inertia about z axis, which is perpendicular to plane of that object or plane of that body, is equal to moment of inertia about x axis plus moment of inertia about y axis, where x and y axis are in the plane of that body and mutually perpendicular to each other. Correct? Mutually perpendicular to each other. Z axis is perpendicular to x as well as z axis is perpendicular to y. Now this theorem is known as perpendicular axis theorem. Here we will have to take some care. The perpendicular axis theorem is applicable only for the planar object. Correct? Only for the planar object. Then and then only we can use this type of formula. Now with help of this, it is possible to determine the moment of inertia of a rod, of a ring, of a cylinder about different axes. Now, for a rod, we are aware about its moment of inertia about axis passing through its center and perpendicular to it. Now this formula is 1 upon 12 ml square. We are aware about that. Now one more homework for you. You may determine the moment of inertia about this axis, that is the axis passing through its edge. They are parallel to each other. Therefore it is possible for you to determine this using the parallel axis theorem. Think over it and try to derive the formula. You may think about the moment of inertia about an axis passing through this particular point, that is if total length is L, then L upon 4 at a distance of L upon 4, the total length is L, correct? Total length is L. It is axis passing through L upon 4. Try to derive the expression for these two moment of inertia, correct? Using the parallel axis theorem. Similarly, if there is a ring, now this is a ring, therefore I am showing that it is in the form of a ring, and I am interested in, or I am aware about its moment of inertia about its axis, and it is mr square, correct? Where m is the mass, r is the radius. Here m is the mass, l is the length. I know the formula for moment of inertia of a ring about its axis. Now try to determine the moment of inertia about an axis which passes through edge of the ring and perpendicular to the plane. Correct? Perpendicular to the plane. Again, I can use the parallel axis theorem. Now try to derive the moment of inertia of the ring about an axis which is along the diagonal or diameter of the ring. Correct? This is the diameter of the ring. Okay, therefore, what is the moment of inertia about this thing? Here we will have to use the perpendicular axis theorem, and one more point is to be used. Moment of inertia about this diameter and moment of inertia about this diameter both should be same, because there is no distinguish between two diameter of the circle or the ring. And therefore, if I1 is the moment of inertia about this, same should be the moment of inertia about this. But this is perpendicular to these two and ring is the planar object. Hence, I will have to use the perpendicular axis theorem. Now try to determine the moment of inertia about this axis using perpendicular axis theorem. And in the similar manner, suppose this is a ring, this is a disc of mass m and radius r. We are aware about its moment of inertia about its axis, and it is half mr square. Now derive the expression for moment of inertia about the axis which is passing through the edge and perpendicular to the disc. And second thing, which passes through the center and it which is in the plane of the disc itself. Now one more possibility is here. In case of a ring, I may think about this axis, where first of all I will have to use the perpendicular axis theorem and then parallel axis theorem. Remember that parallel axis theorem is applicable for any shaped body. But perpendicular axis theorem, the planar body is essential. Same thing here. I may determine the moment of inertia about this particular axis, which is the axis in the plane of the disc and tangential to the disc, passing through the edge. Correct? Now this can be treated as homework for you. Now I will avoid the homework something like this. That means it is a cylinder. I am aware about the moment of inertia of a cylinder about its axis. It is half mr square, where m is its mass and r is its radius. I can use the parallel axis theorem, but it is not proper to use the perpendicular axis theorem. Therefore, I will keep this aside right now. We may think about how to determine these moment of inertias by using some other theorem later on. Right now, this can be treated as the homework for you. Thank you.